Welcome to this video lecture on energy analysis of cycles. Cycles are very commonly encountered in thermofluid systems, so we need to spend a little bit of time on it. Go ahead and take a look at your screen. What you'll see on the screen here is a power plant, perhaps a gas-fired power plant or a coal-fired power plant. This is one of the types of cycles we'll be talking about today. It's an example of a power cycle. Power cycles are used to generate power, generate work. And it's one of many different types of cycles that we will talk about. The other ones that we'll talk about in addition to power cycles will be refrigeration cycles and heat pump cycles. Air conditioners can be thought of as a type of refrigeration cycle as well. Rather than making the interior of your refrigerator cold, the purpose of an air conditioner is to make the interior of your house cold. So an air conditioner is like having a big refrigerator for your house. So let's go ahead and get into the details of it. Now, the first thing we ought to do is define what a cycle is. Okay, so what do we mean by a thermodynamic cycle? The cycle is a sequence of processes that begins and ends with the same state. So to illustrate that, let me just draw a PV diagram. And I'll just draw some arbitrary thermodynamic cycle. Let's say we're starting at this state, state 1. Now, one thing that's important to keep in mind is that properties are only a function of the current state. They have no history dependence on them. Heat and work depend on the history. They're path dependent. Properties are not path dependent. So when we're at state 1, all the properties are exactly the same. If we go from state 1 to some other state and then back to state 1 again, when we come back to state 1, the properties will be exactly the same as they were when we started there. So if we start at state 1 and let's say go to state 2 here and state 3 here. I'm just drawing some arbitrary set of processes. Let's go to 4, go to 5 here, and then back to 1. Then that is an example of a thermodynamic cycle, because what we've done is we started at state 1, we visited some other states, but eventually we came back to state 1. So when we get back to state 1, all of the properties are back to what they originally were. Now the heat and work, those aren't necessarily zero again. Those are path dependent. The heat and work depend on exactly on what the path looks like, but the properties like pressure, specific volume, internal energy, enthalpy, all those values will be exactly the same when we get back to state 1. Okay? So what that means is when we analyze the first law, when we do that for a cycle, since we start and end at the same state, the total energy for our system will be 0, and this is specifically for a cycle. Over the course of a cycle, that total energy, which is a property, will come back to its original value, and so the change in that total energy will come back to being 0 when we go through the whole cycle, when we get back to the original starting point. So what that means then is that the Q into the system over a cycle will equal the work done by the system over the cycle. So from our first law, we know that over the course of a cycle, the energy transferred via a heat transfer and the work generated will be the same over the whole cycle. Now, when I write it down, when I deal with cycles, I probably should be careful and write down subscript cycle to be very precise, but it's cumbersome to keep that subscript around. So I won't write subscript cycle. It's just keep in mind when we're dealing with thermodynamic cycles, we mean the heat transfer and the work over the whole cycle. Now, there are 3 common cycles that we'll deal with. The first one's a power cycle, and then the other 2 are refrigeration cycle and a heat pump cycle. So let me talk about power cycles first. Now, there are many different types of cycles that can generate power. So one might be the type of cycle that you would find in a power plant. Often that involves what's called a Rankine cycle. Another might be a cycle used in an internal combustion engine. That might be a diesel cycle or an Otto cycle or a mixed cycle, combined cycle. Another one might be a Brayton cycle, which is found when you're dealing with like jet engines, for example. So the details of those kinds of cycles we'll discuss in future lectures. All we need to know right now is all those cycles generate power. They just do it using different combinations of the different components, and the details of how they generate power are a little bit different, But our analysis today will be very general. We just need to know that they all generate power. And the way they do that is, in a very general sense, is they all get energy from a hot reservoir, as I show on the screen here. A hot reservoir, what that means is it's a place where you can extract energy that we put into our system. So an example might be in a combustion process. Like if we have a power plant that's burning natural gas, when we burn that natural gas, it generates during that combustion process, a lot of heat is released, right? And we pull heat out of that combustion process. We'll call it Q dot H. It's the rate at which we're pulling heat out. And we'll pull that energy out of this combustion process. The combustion process is our hot reservoir. If it was a nuclear reaction, then the Q dot H, the energy we get out of it, is through the nuclear reaction. If it was a solar power plant, we would get our Q dot H from the radiation, the solar radiation. It's where we're getting our energy from. Now, when we use the term reservoir, what that means is it's when we pull the energy out, the temperature that's generating that energy doesn't change. So it's kind of like some huge, vast reservoir of energy, right? So when we pull the solar energy out for our Q dot H, when we get that energy out of the electromagnetic radiation, we're not seeing a big change in the output of solar energy from the sun, right? It's so big that the Q dot H isn't going to change. The temperature of the sun's not going to change. We're not going to change our Q dot H. Same sort of thing when we talk about burning fuel in a power plant, like burning coal. We're going to assume that there's enough coal being burned that when we pull the energy out, it doesn't decrease the temperature in the combustion chamber. Okay, so that's what we mean by a reservoir. So what we're going to do is we're going to pull some energy out of that hot reservoir, and then that goes into our system. Now the system is where all the details of the different devices are in there. So for example, a typical power plant operation would have like our heat exchanger that goes into a turbine. Of course, we have a shaft coming out of the turbine that goes into another heat exchanger, and then that goes into maybe a pump that cycles some energy that goes into the pump to keep it running, and then it goes around. So you'll see in here, in a typical power plant operation, we might have a couple of heat exchangers, a turbine, a pump. Those are the details. Okay, now if you're dealing with a gas-fired power plant or an internal combustion engine or a gas turbine engine, these details may look a little different. Okay. In our analysis today, we don't need to know what those details are. We're going to keep it general. But I'm just drawing this little picture here to show you that that's where all the details are. Okay, how our system operates, it's all contained within the system. But we're not going to worry about the details of that today. So I'm going to erase it all and just say that we have some system that ultimately extracts power out of the energy that comes into it. So there's some energy coming in, and then we get some power coming out of it. The whole function of a power cycle is to pull some energy out, right? Now, one of the things you'll learn when we talk about the second law of thermodynamics is we can't just end our power cycle there. We can't just have a hot reservoir, a system, and then power out. We have to unload some energy to the surroundings, or to a cold reservoir. So there will always have to be a Q dot C that leads into a cold reservoir. So we put some energy in from the hot reservoir, we extract some power, and as you'll learn from the second law of thermodynamics, some energy has to come back out, and that goes into what we call a cold reservoir. Now the cold reservoir would be something that's cooler than whatever the system is operating at. So it could be the surrounding atmosphere, just the surrounding air. Often it's a body of water, like if you're dealing with a power plant, like for example, the picture we started with, you'll notice that this power plant is right next to the ocean. The ocean, of course, is a cooler temperature than what the power plant is operating at. So there's always some reservoir that we offload some heat transfer into. Okay, we have to have that. And again, that cold reservoir is typically surrounding air. Could be a large body of water like a lake or the ocean. Could be the ground. It has to be something that we offload some energy into. And that just is required from the second law of thermodynamics, which we just haven't talked about before. So we'll call that rate of heat transfer into that cold reservoir Q dot C. Okay, so this is a very general picture. All of the details of how this process works really are contained within the system part, but we'll save that detail for future lectures. At this point, let's just do a first law analysis on the system. So what we're going to do is draw a little control volume around the system, and then we'll do a first law analysis of that. So we'll write out the first law. I've written it in its rate form. Since I have it in terms of Q dot and W dot here, I'll just leave this in terms of the Q dot and W dot. By the way, you can do all of this analysis using just heat and work. It doesn't have to be a dot. You could just have Q, H, W by, and QC without the dots. All the analysis looks the same. So here's our first law. Just a couple of things we can do to simplify. First of all, since we're operating over thermodynamic cycles, this term will be 0. Because it's a cycle, which means that the total energy goes back to being 0 over the cycle. That just goes back up to this idea right here. So that goes to 0. These terms are 0 because there's no mass transfer across this. Now within our system, there's some working fluid in there like water that turns into steam and back into water, like for example in a power plant. Those, all that working fluid and stuff all just stays within the system. There's no mass transfer across the boundaries. So those terms are 0. And so what we're left with then is the power that we extract out of our system is equal to the net rate of heat transfer into our system. The Q dot into, we can expand into a Q dot H minus a Q dot C. Right, because the net heat into our system, or into our control volume here, is the Q dot H coming in minus the Q dot C going out. So just from our first law analysis, we'll see that for any power cycle, it doesn't matter whether it's a power plant, an internal combustion engine, whatever, or what kind of power plant it is, the power that we can get out of that cycle will be equal to the rate at which heat comes into it minus the rate at which heat comes out of it. And of course, if we want it to be an effective power cycle, we want this to be greater than 0, which means that Q dot H, of course, has to be bigger than Q dot C. I mean, that's the whole point of a power cycle, is you want to get power out of it. So the Q dot H has to be bigger than Q dot C. So just a very simple expression, and it's true for any kind of power cycle, right? It's just, we have to have, this is the relationship between work and heat in any sort of a power cycle, okay? We don't need to know the details of how that power cycle operates. Now, since there are all kinds of different power cycles that we could choose from, one thing that we might be interested in is being able to compare how effective different power cycles are. Because typically what we want to have as engineers is we want to get as much power out of that power cycle as we can get for as little cost, right, as possible. So we'll define what we call a thermal efficiency for that power cycle, and we'll give it the symbol eta sub power, or just eta. We're going to define it in the following way. We're going to put the power that we get out of it in the numerator, because we're trying to maximize that, right? We're trying to get as much power out of the power cycle as possible. And then the cost, the thing that we're trying to minimize, is the energy we have to put into it, the Q dot H, right? The way to think about the definition here is we're trying to maximize the power we get out while trying to minimize how much energy we have to put in. The Q dot H is where our costs are. If you look up here, remember the hot reservoir would be where we're burning fuel, for example, like nuclear fuel or coal or natural gas, right? That costs money. We're burning that fuel in order to get a bunch Q dot H here. So ideally, we would not have to burn very much fuel. We would try to minimize Q dot H while maximizing the power out. And if we can do that, then our efficiency will be as large as possible. Now we can make use of our first law expression here and substitute in for W dot by. So that would be what? Q dot H minus Q dot C all over Q dot H, which we can then write as 1 minus Q dot C over Q dot H. So that is our expression for the thermal efficiency. And now we can compare different kinds of power cycles to see which ones have a better efficiency. Now when you look at that expression, you'll see here that the Q dot H is larger than Q dot C. And so what that means then is that this ratio will be less than 1, which means 1 minus that will also be less than 1. So our efficiency, thermal efficiency, will always be less than 1. Now, again, when we talk about the second law of thermodynamics, what you'll find is that Q dot C cannot be 0. It always has to be some positive value, right? So you can't have the Q dot C equal to 0 and have a thermal efficiency of 1, so that's not possible. Okay, so we'll show from the second law that the thermal efficiency always has to be less than 1. It can never be 100%. All right? So that's how we define the thermal efficiency. It's easy to remember if you just think about, we're trying to maximize the power while minimizing the cost, which would be the Q dot H. That's what we have to do. We have to supply that Q dot H, and that costs money. Okay, and just to kind of give you a feel for what typical thermal efficiencies might be like for practical applications, if you have a very efficient power plant, like a gas-fired power plant, that thermal efficiency might be on the order of about 40%. That's pretty efficient. For an internal combustion engine, we might be looking at thermal efficiencies on the order of 20 to 30%. So in terms of thermal efficiency, we're pretty far from 100%. But as you'll see later, again, when we talk about the second law, we're not too far from the maximum theoretical efficiency that we can get. I'm saying that the thermal efficiency here has to be less than 1, but when we talk about the second law, we'll show that it's actually dependent on the temperatures of the hot and cold reservoirs. And it's the maximum thermal efficiency you could possibly get is actually much less than 1. But we'll save that for a different lecture. So those are power cycles. Let's now talk about refrigeration and heat pump cycles. Now the general picture we'll use for those looks much the same as what we did for a power cycle. We still have a hot reservoir, a system, and a cold reservoir. Again, the system is where all the details of the refrigeration or heat pump cycles or air conditioning cycle. An air conditioning cycle, again, is very much like, it's identical to like a refrigeration cycle. But all the details of how, the compressor, the refrigerant, the radiator, all those things are contained within the system. But we're not going to worry about those details here, not in this lecture. So the way a refrigeration cycle works is we have our cold reservoir. That's what we're interested in. That's like the interior of your refrigerator. Or if it's an air conditioner, it's the interior of your house. We're trying to make that cold, right? So that's our cold reservoir. And we'll pull some energy out of that cold reservoir. We'll call it Q dot C, and it goes into our system, goes into our components within our refrigerator, like the compressor. That's really the working fluid inside your refrigerator, which would be like a refrigerant that moves through the compressor and the radiator and so on and so forth, the pump and all that. So that's the Q dot C. That's the energy we're pulling out of the interior of our refrigerator. In order to pull that energy out, we have to do some work on our system. So our control volume just, again, surrounds the system here. We have to put some energy in to remove that heat. So this is why you have to plug in your refrigerator or plug in your air conditioner, because we have to do some work to pull that heat out of our cold reservoir, and then we move some of that energy into a hot reservoir. That's the Q dot H. Again, we have to do that, as you'll see from the second law of thermodynamics. And the hot reservoir, if you're dealing with a refrigerator, the hot reservoir would be the room, basically the kitchen. So you're pulling energy out of that cold compartment within your refrigerator, and that energy ultimately makes its way into the kitchen, into the surrounding room. That's why you'll see a radiator on the back of your refrigerator. It's so that we can pull the energy out of the food and air that's within the refrigerator, and then that energy goes out through the radiator into the surrounding room. If it was an air conditioner, you'd be pulling the energy out of your house, and then that goes out through a radiator out into the surrounding air, like the air outside. So that's how a refrigeration cycle works. For a heat pump, the way heat pumps work is you're actually pulling energy from the outside and bringing it into your house to warm it up. So the cold reservoir for a heat pump cycle would be the surroundings, like the surrounding air outside your house. Often it's the ground, or maybe a body of water like a lake, or groundwater underneath, deep, in a well or something like that, deep under the ground. But you're pulling energy out of those surroundings, and you're taking that energy through your heat pump. You have to put some work into your heat pump, and moving that energy into the hot reservoir, which in this case would be the interior of your home. So heat pumps operate by taking energy from the outside and bringing it to the inside of your home. So it's the same idea as a refrigeration cycle, but it's important to know that the goal is different. In a refrigeration cycle, you're trying to cool down the cold reservoir as much as you can, whereas in a heat pump cycle, you're trying to put as much energy as you can into the hot reservoir. Okay, and we'll talk about these cycles in more detail, like I said, in future video lectures. So we can do a first law analysis just like we did with the power cycle. So in this case, we'd have, again, I'm not going to put all the steps, but just like what we did with the power cycle, what we'll end up getting when all is said and done with our analysis is that the power that you have to put into your system is equal to minus the Q dot into the system. Okay, that just comes from our first law analysis, keeping in mind that the change in total energy over the cycle would be 0. The Q dot into, in this case, would be the Q dot C minus Q dot H. So then the work, or the power that we have to put in, would be equal to Q dot H minus Q dot C. So that's what we get from our first law analysis. And then let's talk now about how we define efficiencies for refrigeration heat pump cycles. So instead of using the term thermal efficiency, historically what we use is a term called coefficient of performance, or COP. So you can see it right here. So coefficient of performance is just like an efficiency, but for a refrigeration cycle or heat pump cycle. And so the way we define a coefficient of performance for a refrigeration cycle, essentially an efficiency for a refrigeration cycle, is Q dot C divided by the power that we have to put in. Now, the reason we define it like that is because what we're trying to do in a refrigeration cycle is we're trying to maximize the amount of heat energy that we pull out of the cold reservoir. Again, think about the cold reservoir being the inside of your refrigerator. You want to get as much energy out of there as you can. So you want to maximize your Q dot C, and you want to do that for having to put as little power into your refrigerator as possible, right? You don't want to have to use that much electricity. So that's how we define that coefficient of performance. And we could, of course, make use of our first law expression here, expand that out. So we could write it like this, or divide through by the Q dot C, Q dot H all over Q dot C minus 1. So we could make it look like that, for example. So that's just another way to write out the coefficient of performance. I think it's probably easiest just to remember this yellow highlighted bit. You don't have to memorize. Again, I'm not a big fan of memorizing equations, but I like to think the way that I would remember this is just what is it you're trying to accomplish. You're trying to get as much heat out of the cold reservoir, the Q dot C, for as little power that you have to put into it. And then to get down to this expression or this one, you just use the first law. Okay. Now for the coefficient of performance for a heat pump, the way we define that efficiency is, I'm going to have to erase this so we have enough space, is it'll be Q dot H all over W dot on. It looks a little different. Now the reason for that definition looking different is because the goal of a heat pump is a little different. In a heat pump, we're trying to put as much energy as we can into the hot reservoir. So again, remember, for a heat pump, the hot reservoir is the interior of your house. The cold reservoir would be like the ground or the surrounding air, for example. So in a heat pump, you're trying to maximize how much energy you get into your house. So you're trying to maximize Q dot H, and you want to do that for as little power in as possible. So that's why it's Q dot H over W dot on. So larger coefficients of performance result in more efficiency. Okay, so you want really large coefficients of performance. And of course, again, we could use our first law expression if we wanted to expand this out. If we want to put it all in terms of the rates of heat transfer. And now typical values for coefficients of performance for a refrigeration cycle. So a typical value might be on the order of 1.6 to 3.1. Coefficient of performance for a typical heat pump cycle might be on the order of 3 to 4. They're defined differently, right? There's a Q.C here and a Q.H there, so you'll see different values. So those are typical values. Now, the efficiency, thermal efficiency up here, coefficients of performances down here, these are all dimensionless quantities. They have no units associated with them. Okay, they're just numbers like 1.6 and 3.1. Now, in practice, like if you actually went out to buy a heat pump or buy a refrigerator, you won't see people using the term coefficient of performance very much. Coefficient of performance is much more of an academic term. We use it. It's well defined in academia. It's dimensionless. It's easy to use. Unfortunately, in real practice, people have used other terms that have a terrible set of units associated with them. So one very commonly used quantity is called an energy efficiency ratio, EER, and the way that's defined, now just bear with me because it's awful the way it's defined. EER, the energy efficiency ratio, is defined as the Q dot divided by W dot. Okay, so this would be, again, Q dot C or Q dot H, depending on what you're interested in. This is the power in. So it's just like what we define the coefficient of performance as. However, in the United States, the Q dot is in BTUs per hour. Okay, so that's an English unit. So that's the rate of heat transfer in English units. So that already is kind of awful. But then the power in the denominator is in watts. So that's a metric unit. So now we have mixed units, the English system and the metric system all combined together. So that's how the energy efficiency ratio is defined. So it looks just like the coefficient of performance, but rather than being dimensionless, you've got a weird set of units that combines both English and metric units. So it's terrible. And if you want to get the actual conversion here, I show it here. So this is how you convert from a coefficient of performance into an EER. So you have to multiply it by this ratio, this 3.41214 BTU per watt hours. It's awful, but it's just the way it is, and that's the common quantity that you'll see in the U.S. And larger EERs result in more efficiency, okay, because it's proportional to the coefficient of performance. So we want large coefficients of performance, so it means we want large EERs. Now, when you deal with air conditioners, often those are talked about in terms of capacity. So they'll talk about a 4-ton capacity air conditioner or a 1-ton capacity air conditioner. This one's also an awful type of unit. So capacity is given in kilowatt per ton, where 1 ton is 12,000 BTUs per hour. So it's kind of like kilowatts like your power, and the ton would be like the heat transfer here, BTUs per hour, except 1 ton is 12,000 BTUs. Now the ton here it's related to mass. It's a historical term. It comes back to the idea when people were interested originally in cooling, they did cooling using ice. Okay, and so the idea here is that 1 ton of ice did a certain amount of cooling over a 24-hour period. And so the 12,000 BTUs per hour is how much energy over a 24-hour period it would take to melt 1 ton of ice. Okay, so I know it's a terrible unit to use, but it's historical and it's somehow stuck around for a long time. It would be much better if we used coefficient of performance. It's a nice, well-defined quantity with dimensionless, so it works whether it's metric or English units. But for historical reasons, you'll often see air conditioning given in terms of capacity. Anyway, we won't work with EER or capacity in this class at all. We'll just stick with the COP because it makes a lot more sense. And but I just want you to be aware that this is the unfortunate set of units that at least they use in the United States. Okay, I think that covers everything I wanted to talk about with regard to energy analysis of cycles. So just to recap again briefly, when we talk about a cycle, it means that we're starting from some original point and then we come back, we go through a number of different states, but we come back to the original point. So over that cycle, the properties remain the same. And so the total energy ends up being zero. The change in total energy ends up being zero over the course of a cycle. So that's why we had the heat and work being equal to one another. The cycles that we'll deal with are power cycles, which generate power, and refrigeration and heat pump cycles, which move energy around. We have to put power into it to move the energy around. We defined a thermal efficiency for power cycles and said that that efficiency has to be less than 1. We defined coefficients of performance for heat pump and refrigeration cycles. They're different from one another. Those coefficients of performance have to be greater than 1. And one thing I just want to emphasize is that we did all this analysis using a very general kind of picture here involving hot and cold reservoirs in our system. We can get a lot out of these very generalized pictures without needing to know the details. That's one of the great things about control volume analyses is you don't need to necessarily know the details of what's happening inside the control volume. You're just relating to what's happening as you cross boundaries of the control volume, as you cross the control surface. Okay, we'll go ahead and end things there.